Hello engineers, welcome to the new video of the course, and in this particular video we are going to understand the difference between conductors, insulators and semiconductors based upon energy band diagram. So I had specifically mentioned that we are going to differentiate them based upon the energy band, based upon their energy band diagrams. Okay, alright. So as you can clearly see in this particular image that this particular energy band, it is representing conductors. This particular energy band diagram, it is representing semiconductor, and this particular energy band diagram, it is representing insulator. So what we can conclude, just by looking at this particular image is that, see, you can just see that band gap of insulator, it is quite high, that is Eg, right? If you could remember, I had specifically mentioned in my previous two sessions back that this particular gap, it is also known as forbidden energy gap, which is represented as Eg, right? Eg, something like this. So it is also represented as Eg. So Eg is quite high for insulator, then as compared to insulator it is quite low in case of semiconductor, or in case of conductor it is negligible, right? So you can clearly see this is our energy, and the energy band diagram, or energy gap, or the forbidden energy gap, it is negligible in case of conductors. Okay, so we are going to discuss each and every diagram, okay, in detail way. So let's proceed further. Okay, so now since we are in conductors, right, and just remember one thing, as I had mentioned that this is my valence band, and in valence band we have lots of electrons. So let me just write this particular electron, let me just show this particular electrons little below. Yeah, so there are lots of electrons present in the valence band, right? And there are hardly any electrons present in the conduction band. Let me just show you one electron. So there is only one electrons present in the conduction band. Okay, so let me just write over here that this is my conduction band. This is my conduction band. Okay, and this is my valence band. This is my valence band. Valence band. Okay, great. Now as we had already seen, or rather as I had already mentioned, that the energy gap, or Eg, for conductors, it is how much? It is almost negligible. I can show it in this way, that is Eg, it is almost equivalent to 0 electron volt. It is almost equivalent to 0 electron volt. Okay, great. So now if you look over here in case of conductors, what is going to happen? See, just by supplying very less energy, very less energy, this energy can be anything. Maybe since we are dealing with semiconductor, so we can supply voltage to our conductor device. So this particular conductor, it can be anything. It can be a iron material, it can be sodium, it can be anything, right? I mean, obviously it should be a metal since it is a conductor, right? Or basically if we provide certain heat, then what is going to happen? Just see over here. So majority of the electrons which are present in this particular valence band, they will move from valence band to the conduction band. Okay, they will easily move from the valence band to the conduction band. So majority of the electrons which were present in the valence band, they will move to the conduction band. And that's why, if you could remember, in our previous session I told you that the electrons which are present in the conduction band, they are responsible for the electrical conductivity, or they are responsible to generate the current. So this is the reason behind that, right? Because now if you look over here, the electrons present in the conduction band, they are free electrons, right? So just by providing very less energy to this particular electrons, we can actually generate current from this particular electrons. Okay, so that's why in the if you could remember, in the previous session when we were focusing upon the modified definitions, that is modified definition of valence band and conduction band, over there I had clearly mentioned that the electrons present in the valence band, they are not at all responsible for the formation of current, or to generate the current, whereas the electrons which are present in the conduction band, they are solely responsible for the generation of current, or for the electrical conductivity. And this is the reason behind that. Why? Because just by supplying very less energy, so this energy can be anything. It can be a thermal energy, it can be a it can be an electrical energy, it can be any energy, right? As I had mentioned, voltage or heat. So due to this, what is going to happen? The electrons, they will lose certain energy and they will move to the conduction band. The electrons will move from valence band to the conduction band, okay, and again by supplying very less energy as well to this particular electrons, as they are free, so due to which the electrons will start moving, or the flow of electrons will start in the circuitry, and thus we will obtain certain current. I know still you might find it little difficult to understand, but just try to understand, okay. So now let me proceed further in case of semiconductor, because for us the semiconductor is the most important topic, right? So now let me move over here. Again, this is our valence band. So this is my valence band, valence band. This is my valence band, and this is my conduction band. This is my conduction band, okay. This is my conduction band, and over here the Eg that is available, that is energy, forbidden energy gap, it is quite high as compared to the energy gap which was present in case of conductors. Practically or technically speaking, it is around 3 electron volt for semiconductor. For semiconductor, the forbidden energy gap, or Eg, it is around 3 electron volt. Roughly it is around 3 electron volt, okay. If it is less than that, that is also fine. That will also come under the category of semiconductor, okay. Great. Now again, I'll just draw the electrons. Over here I'm drawing certain electrons, okay, which are present. Obviously, since this is our valence band, so there are lots of electrons that are available over here. And now what is going to happen? See, if I provide certain high energy, okay, or in this particular scenario we need to provide little high energy, okay, as compared to the earlier case, okay. Energy, just for your understanding purpose, let's suppose if we are providing energy of maybe 1 joule, something like that. So over here we need to provide energy of 5 joule, something like that, okay. So basically our energy is increasing this time, okay. So again, this particular energy, it can be anything. It can be a thermal energy, or it can be a electrical energy. It can be any quantity, right? So I'll again write it as heat, or it can be a voltage source. It can be a current source as well. It can be anything. As of now, we don't need to focus upon that. Now what is going to happen? Over here, the electrons will travel from valence band to the conduction band, but this time the quantity of electrons that will travel from valence band to the conduction band, it won't be that much. It will be present, I mean the electrons will migrate from the valence to conduction band, but their quantity would be little less, okay. So you see, the electrons are migrating from the valence band to the conduction band, but only 4 electrons out of whatever that 10 or 15 electrons are present. So out of 10 or 15, only 4 electrons are migrating, whereas if you see over here, out of 10, almost 6 electrons were migrating from valence band to the conduction band, and this was when we were actually supplying very less energy. On contrary, if you look over here, we are providing slightly higher energy as compared to the previous case, but over here only 4 of the electrons are migrating, or they are able to move from valence band to the conduction band, okay. And I would like to highlight one more point, okay. Although I had just given this as a rough estimation, like the energy won't be in joules, but this is just for understanding purpose, right? When we actually try to take the all those mechanical quantities into the electrical one, so it would be pretty easier, or rather it goes pretty easier to understand or to comprehend these concepts of electronics and all, okay. So let me just highlight one more point over here. So let's suppose whatever the energy that I'm applying over here, so I'm talking about this particular energy, okay. So if this energy, if it is less than maybe 3 electron volt, something like that, so in this particular scenario, what is going to happen? The electrons will remain in the valence band only. So the electrons will remain in the valence band only. Majority of the electrons will remain in valence band. On contrary, whatever the energy that we are providing or that we are applying, if it is quite greater than 3 electron volt, So in this particular scenario, this electron will move out of valence band, and it will actually across this particular forbidden energy gap as well. So during this particular scenario, the electrons can easily migrate or move, whatever you want to say, from valence band, I'm just writing it in short form, to conduction band. Okay, conduction band. Okay, and after, again, we need to provide certain energy to these particular electrons as well, which are present in the conduction band. And when we provide them certain energy, so obviously the flow of electrons starts, and thus the current is able to generate, or rather we are able to generate the current. Okay, great. Now we will focus upon the insulator. What exactly will happen in case of insulator? So in case of insulator, you see this particular Eg, this time the Eg is quite high. Okay, that is the forbidden energy gap. So over here, the forbidden energy gap in case of insulator, it pans out to be around 6 electron volt. 6 electron volt. So it is quite high, or it is the highest as compared to the other two cases, or the previous two cases, that is as compared to conductors and the semiconductors. So again, I'll just draw certain electrons over here. So I'll just draw few electrons over here. Okay, and now even by providing very high energy, over to this particular conduction band, valence band, valence band of insulator. So let's suppose over here I'm providing 10 joule of energy. Okay, I'm just taking a random number. Over here I'm providing 10 joule. Over here, let's suppose if I was providing around 5 joule, and over here let's suppose if I'm just providing 1 joule, right? So just see over here, even though I'm applying very high energy to this particular valence band of the insulator, but still the electrons are not able to cross this particular energy band, forbidden energy gap, and they will prefer to remain as it is. So basically what is happening over here? So if you look very clearly, the electrons which are present in the valence band, they are unable to migrate, or they are unable to move to the conduction band. Okay, so in case of insulators, the electrons cannot move from the valence band to the conduction band, and that's why if you could see, let's suppose if I'm applying certain voltage to the wood, okay, so the wood won't allow the current to pass through it, or rather it won't allow the electrons to flow through it. Why? Because the electrons of the wood, okay, that means in the conduction band of the wood, okay, or you can take any other material which is an insulator, maybe a glass, maybe a diamond. Okay, I had taken a wood, or you can also take diamond. So the conduction band of the wood or a diamond, they don't have enough amount of electrons present in the conduction band. Okay, so again I will repeat, in case of insulator, freely available electrons are not present in the conduction band. Okay, so that's why even if we apply certain high energy, let's suppose if I'm providing maybe 10 volts, 20 volts, 30 volts, 50 volts to the insulator, maybe a diamond, maybe a wood, maybe a glass, okay, anything. So electrons won't flow through it, and since the electrons are not able to flow from that particular insulator, okay, so therefore the current remains straight away 0. So that is the idea or logic behind the insulator. Okay, so let me just write over here, the electrons cannot migrate. Let me change the color. Yeah, electrons cannot move from valence band to conduction band, and due to this what is going to happen? Therefore freely available electrons, therefore there are negligible electrons in conduction band, and thus this is the actual reason the current I is 0 ampere, That means therefore the current does not flow from the insulator. Why? Because there aren't any electrons available in the conduction band of insulator. And why? Because the energy gap or the forbidden energy gap, it is quite high. As you can see, it is around 6 electron volt. So even by applying very high energy to the valence band of this particular insulator, the electrons cannot migrate, or the electrons cannot jump from valence band to the conduction band. And that's the reason that why exactly the current cannot flow, or rather why exactly the insulators are the bad conductors of electricity. Okay, why the insulators are the bad conductors of electricity? Okay, this is the actual reason, because the electrons cannot move from valence band to the conduction band. And why exactly it can't move? Because of this particular forbidden energy gap, which is quite high as compared to semiconductors and conductors. Okay, so let me just give you one more example. But before that, okay, I had not inserted one diagram. Just a second, let me just insert one diagram, and that would be like a conclusion for this particular session. Just a second. Yeah, this is that particular diagram. Yeah, let me just zoom out this particular diagram. Alright, so you can clearly see over here. See, as I had mentioned that in case of conductors, if you look over here, majority of the electrons which were available over here, majority of these electrons migrated from valence band to the conduction band. Okay, majority of the electrons migrated from the valence band to the conduction band. Okay, now in case of semiconductors, few of the electrons only, not majority, but few of the electrons will be able to migrate from or jump from valence band to the conduction band. Only few of the electrons, maybe as I had mentioned that maybe 5 out of 10 electrons would be able to jump from valence band to conduction band, whereas in case of conductors, maybe 8 out of 10 electrons were able to jump from valence band to the conduction band, because the energy gap or the forbidden energy gap, it is straight away 0. Whereas in case of insulators, you see, none of the electrons is able to surpass this particular energy gap or the forbidden energy gap, and therefore all of the electrons will remain as it is in the valence band only. Okay, and therefore insulators are the bad conductors of electricity, whereas semiconductors, it can actually execute both of these particular properties. If I, as I had mentioned, if I altered certain parameters, I hope you all guys can remember that particular session wherein I had shown you the example of diode. If the voltage of diode, if it is less than 0.7 volts, so it was acting as an insulator. On contrary, if the voltage of diode, if it is quite higher than 0.7 volts, then it was acting as an insulator. So basically what I want to convey to you all guys is that, see, when I say maybe those guys who have good idea about diodes, for them they can actually understand this particular, or they can actually grasp this particular concept in the proper way. But if you don't have any idea about diodes, don't worry, just try to understand it. Okay, so when the diode voltage, so let's suppose this is my diode. Okay, and let's suppose the voltage that I'm applying over here, let's suppose this is my voltage V, and let's suppose this particular V is maybe 0.3 volts. Let's suppose it is 0.3 volt. So obviously, diode voltage is how much? So this is my diode voltage. Diode voltage is 0.7 volts. Okay, so the diode voltage is 0.7 volts, and the voltage that I am applying, it is 0.3 volts. So we can clearly see that my V, it is less than VD. Okay, so what does that mean? That means if you look over here, so basically what does that mean? That means the energy means what? The V. Okay, we are talking about V, which is, let me change the color, man. Which color should I take? I'll go with white only. Okay, yeah, so our V, which is a 0.3 volts, it is less than 0.7 volts. So what does that mean? That means try to actually relate this particular condition with this one. That means whatever the energy that we are applying, so in this case we are applying 0.3 volts, right? It is less than the this particular forbidden energy gap. So basically the electrons which are present in the valence band of that particular diodes, they are not able to move from valence band to the conduction band, because they are not able to surpass this particular forbidden energy gap. Okay, but let's suppose just draw it again roughly. Again, let's suppose this is my diode, okay, and this time I'm applying maybe let's suppose if I'm applying 1 volts over here, and we all know the diode voltage is 0.7 volts. So you can clearly see my diode voltage is 0.7 volts. The voltage that I'm applying, it is 1 volt. So obviously V is greater than VD. So what does that means? So this time you can relate this particular condition with this one, wherein what I'm doing, whatever the energy that I'm applying, that means voltage that I'm applying, which is 1 volt, it is greater than 0.7 volt. That is my diode voltage, right? 0.7 volt. Similarly, this was my diode voltage VD. Okay, so basically you can actually try to apply this logic to this particular condition, that is the energy that I'm applying, which is 1 volt, it is greater than diode voltage. That means this particular energy, it is quite sufficient to jump these electrons from the valence band to the conduction band. So whenever we apply this kind of energy to the valence band of the diode, so whatever the electrons that are present in the valence band of the diode, they can easily surpass this particular energy forbidden energy gap, or this particular gap which is present in between valence and conduction band. Okay, great. So one more point I would like to add, I just forgot to add that point, and that is, see, the energy or the forbidden energy gap in case of silicon, the forbidden energy gap in case of silicon, it is 1.1 electron volt. It is 1.1 electron volt. So this is the energy forbidden energy gap of silicon. Then we have the energy gap forbidden energy gap of diamond, which is around 6 electron volts only, so no need to worry about that. So basically the forbidden energy gap for diamond, which is an insulator, it is around 6 electron volt. Okay, so basically it's not necessary that this is the energy band forbidden energy gap. This should be the forbidden energy gap for the insulator. So basically, let me just write it in this way. So the forbidden energy gap for the insulator, it should be greater than 3 electron volt, because in few of the insulator this number would be around 3.5, 3.9, something like that. So not necessary every time you will get 6 electron volt. For diamond it is 6 electron volt. For for the insulators like glass, maybe paper, maybe eraser, whatever that is, this Eg would be greater than 3 electron volts, but surely it can be less than 6 electron volts as well. So you see, if it is greater than 3 electron volts, so it will go in the category of insulator. If certain material, if it's forbidden energy gap, if it is less than or equal to 3 electron volt, okay, that means 0 to 3 electron volts, okay, then it will fall under the category of semiconductors. And the material whose Eg or the forbidden energy gap is straight away 0 electron volt, so then it will fall under the category of conductors. Okay, and there is one more thing to discuss. This it's my promise to you that this will be the last point of the session, and it is quite important. So if you could remember, just 2-3 sessions back, I asked you this particular question, that for insulators what would be the Eg. So now it's your time to answer this particular question, and I believe that you all guys can easily answer this particular question. Alright, so I believe that you all guys might have thought the answer, and the correct answer is this, that is, see this one, option E. Energy gap of forbidden energy gap of insulator, it is greater than the semiconductors and it is greater than conductors. Okay, so let me just write over here, forbidden energy gap of insulator, it is greater than forbidden energy gap of semiconductor, okay, which is greater than forbidden energy gap of conductor. Okay, and what are the values for it? So generally it is saying that the energy gap in case of conductor, it is around 0 electron volt. This is around 0 to 3 electron volt, and this is around, or it is greater than 3 electron volts. Okay, e.g. greater than 3 electron volt, it can be any number. Okay, maybe if you take any other material, so its value would be greater than 6 electron volt as well. Okay, so yeah, this was all about the session, and I believe that you understood each and everything that we had discussed in this particular session, and also the concepts which we discussed in the previous sessions as well. Okay, just have a look at this particular image, and I believe that you understood each and everything that we discussed till now. Okay, so I really hope that you understood each and everything that we discussed in this particular session. But still, if you have any doubts, if you are facing any difficulties anywhere, it's my request to you that you please ask me in the communication section. I will surely help you out there. So thank you for listening me patiently. I'm ending this video over here. Thank you.